Good morning and welcome to Tech 240 on Wednesday, February 24th. I'm going to make a couple of videos today. In this first video, I'm going to show you an example of how a generator actually works. And we'll do a couple of review problems to talk about the shape of magnetic fields and Faraday's law and just review some of the concepts that we've talked about so far. And then in the second video, we'll take some of the pieces and parts of the generators that we've talked about so far and put them together into a real generator that is more realistic for use on the electric grid. But first, I want to show you an example of a generator that I happen to have in my office. So let me move this camera down so you can see this. This is a hand crank generator that works by rotating this crank right here. And a couple of the parts that we have on this hand crank generator. First, we have a magnetic field. It's actually pretty strong. It really is quite a strong magnet. So we have a north pole and a south pole. And then this, you got to be kind of careful when you put that on so you don't pinch your fingers. This goes down on here. And then this part here and this part here are just pieces of steel. And steel has a high magnetic permeability, so this allows the magnetic field to kind of wrap around down here. So this just kind of extends the magnetic field. Then you can see in here, we have a bunch of coils of wire. I haven't counted the number of turns on that coil, but it's a lot. It's probably a couple of hundred. And even though it looks like two separate coils, it's really just one coil. There's a wire that connects these two. So it's just on both sides of the axle. The wire is wrapped around on either side of the axle. But it's just one coil of wire with probably several hundred turns on it. And we're going to start calling that an armature today. And as I rotate this, of course, we have this drive belt, which comes down here. And then that is going to drive the axle right here, and the armature is mounted to the axle. So as I spin this, the armature is going to spin around really fast inside the magnetic field. So what do we have here? Well, we have a magnetic field, we have a conductor, and we have relative motion between them as I rotate this. So whenever we have those three components, we meet the requirements for generator action. And so we are going to get an induced voltage in the wires on the armature. So let me show you the other side of this. I'll show you a few more components. So we've got our armature right here, and then our wires that are coming out of the armature. I hope you can see these. There's a red wire right here, and there's a green wire right here that are coming out of either side of the armature. So we're going to have an induced voltage on the red wire relative to the green wire. And that voltage is going to depend on how fast I rotate this, because how fast I rotate this tells us, or is going to give us a different amount of relative motion. So as I have more relative motion in the generator, I'm going to produce a higher induced voltage in these wires. So then one question, when you go to put this in a real world generator, the question is, all right, I got this induced voltage on this armature, which is rotating around, but I got to get that voltage off of the armature and onto the stationary electric grid. Like here's our outputs, our positive and our negative output right there. So how do I get the voltage from the armature onto the stationary electric grid? We'll talk more about this today and in the future as well when we talk about DC generators. But the answer is that we have these wires connected from the armature to something that is called a slip ring. And this kind of sort of copper looking thing right here is called a slip ring. And that rotates around, that slip ring rotates around with the armature. So as the armature rotates, the slip ring rotates around also. And then you have something that is kind of riding on the slip ring. That's this right here. And that is what we call a brush. It doesn't really look much like a paintbrush, right? But its purpose is to conduct the electricity from the rotating slip ring to the stationary electric grid. So in this case, this top brush is conducting electricity from one side of the slip ring to this part right here, which is connected to the red side of the output. And then the other brush down below on the bottom, you can't really see that, but there is a brush on the bottom there. Now you can see it. there is a brush on the bottom as well, and that is conducting the electricity from the other side of the slip ring. And actually there are two segments in the split ring. I don't know if you can, or in the slip ring. I don't know if you can see that very well, but there are two segments. So really, if this is operating as an AC generator, then this brush should be over here, and this brush should be over here, so that the brushes are connected to different sides or different pieces of the slip ring. All right, so now it's operating as an AC generator. So this side of the slip ring, or this part of the slip ring, is connected to this brush, and the brush down below is connected to the other side of the slip ring, which is connected to the other wire from the armature. All right, so that's how that's working. The other side of the slip ring is connected to this brush down below, which connects to this side of the output. So that's basically how it works. This is kind of a clever design, which makes it a little bit difficult to explain right now because we haven't talked about DC generators yet. But the design of this particular hand crank generator is actually designed to operate as either a DC generator or an AC generator. We'll talk about AC generators first. We already have started. And then in a little bit, we'll talk about DC generators. And there's only a couple of minor things that you have to change to convert from an AC generator into a DC generator. One of those has to do with the slip rings. So you convert the slip rings into what's called a split ring commutator. So initially, the way these brushes were, where they were kind of in the middle of the output here, that's kind of stuck now. There we go. Okay, it slides, not easily, but it slides a little bit. So the way this particular device is kind of designed, it's designed where it can operate as either slip rings or what's called a split ring commutator. And a split ring commutator is what we use for the output of a DC generator. We'll talk more about that in the future. For today, I want you to know that AC generators use slip rings, and we'll talk more about that today. And then in in a couple of class sessions or so, we'll talk about DC generators. And DC generators, one of the differences that they're going to have is that they are going to use something called a split ring commutator. All right, so that's about it for this example. I kind of like this hand crank generator. I actually used these. I used a bunch of these a few years ago now. It's probably 5 or 6, now probably more like 7 or 8 years ago now, where I was working on a project related to the smart grid. It was right around the time when the smart grid was rolling out in Illinois. And it was for a grant, and I made a whole bunch of electric grid dioramas. They were all 4 feet by 8 feet. I made 3 of them, and it was kind of like a train set, kind of. Didn't have trains, but it had generators on it. And then it had some cities that we 3D printed the houses and buildings and stuff for. It had a model of the Willis Tower and apartment buildings and homes and stuff like that. And the idea was that it was built for students, K through 12, but mostly junior high and high school students. And it was built so that the students had to work together to operate these hand crank generators. There were 3 of these on each electric grid diorama. The students had to operate these and work together to energize the electric grid with a voltage that was not too low, not too high, like a Goldilocks voltage that was just right. And that was a pretty cool project. I spent the better part of a year working on that project, but it turned out really well. And actually those dioramas still exist. They're still, well, not this year, but they're traveling around to K through 12 schools all around Illinois, showing them how the electric grid and how the smart grid operates. All right, so that was just kind of a demonstration. I wish it could be a hands-on demonstration. If we were in person, I'd pass this around and you could run it and make noise while I'm talking in the classroom, because it is kind of noisy. It could probably use some grease on the axle here, but it still works, and it's a pretty cool example of a small-scale generator. Of course, For a large scale generator, like a utility scale generator, you basically take that same thing and you scale it up by, about 100 times larger. So if you have 100 times larger than that, then you've got yourself a utility size electric generator that could, produce a significant amount of electric power to put it on the electric grid. All right, so enough about that for right now. Let's go ahead and do some example problems. So what I'm going to go ahead and do is show you the problems. And then what I'd like you to do is pause the video and take a few minutes or however long it takes to come up with your answer for these. And then you can restart the video and we'll go through the answers. All right, and number one, what I want you to do is draw the magnetic field around this electromagnet. So notice we've got a voltage supply or a battery or something right there, a DC voltage, and it's applied such that the positive side's on the bottom, negative side's on the top, and it's wrapped in this direction as shown here around this metal core material. And so this is going to form an electromagnet. But I want you to get some practice thinking about and drawing the magnetic fields around this type of electromagnet. So go ahead and draw that magnetic field. B, you're drawing B by drawing lines of magnetic flux. In number two, we have a generator that's given. And what I want you to do is think about which direction this generator is going to rotate. It's either going to be clockwise in this direction or it's going to be counterclockwise in this direction. But the question is, which one? So use the hand rule that we talked about last time and figure out which direction the armature, that's what we're going to call it, the armature of this generator is rotating. And one more. Here is a practice calculation problem. So we have that generator in problem number 2. Let's refresh your memory. It looked like that, just a simple fundamental generator. We have that generator, the armature, which means the coil of wire, in problem number 2 passes through a magnetic field that changes from 0.5 Tesla to 1.5 Tesla, and that takes 0.1 seconds. The area of the coil is 0.2 meters squared, so you can calculate what is the output voltage at this point in time. Remember, we talked about last time how the voltage is going to change as this thing rotates, but at this point in time, with these given values, tell me what is the output voltage at this snapshot in time. Okay, so take a few moments, pause the video, come up with an answer to each one of these 3 questions, and then you can unpause the video and we'll go through each one of these. Okay, I will assume that you have paused the video and you've come up with an answer for each of these, so we'll talk through these. All right, so in this first problem, we're drawing the magnetic field. That is, we're drawing B by drawing lines of magnetic flux, which are phi. And so in this case, we've got the magnetic field that's going to be going around here. We're pretty certain it's going to be going around here, but we definitely don't know what the polarity of the magnetic field. Which side is the north side and which side is the south side. So let's go ahead and apply the relevant rule. And we know we're going to have current that flows through here from the positive side, through the coil, and then back to the negative side, because current always flows from positive to negative. And so we know that we're going to have current coming down here. So what I like to do is go ahead and apply the right-hand rule for current carrying conductors. Remember, that looks like this. That's our first hand rule that we talked about last week. And go ahead and draw the magnetic field by applying the right-hand rule to this section. I'm going to do this section first, just to kind of as a warm-up and kind of to think about what's going on. So we have current going in this direction. I mean, I can even draw that. In this section of wire, we have current going from left to right. So we have our thumb that's going to be going from left to right. Imagine you have your conductor, you're holding it in your hand, and your thumb is pointing left to right. and then we're going to curl our fingers around that conductor. And that's going to give us the shape of the magnetic field. So it rotates around in this direction like that. And it goes up and back and down in front. So it goes up and back, down in front, and then up and back again. Up and back, down in front, and then up and back again. All right, so that's what the magnetic field looks like in this part of the conductor. I don't really care about this part right here because this is a relatively weak magnetic field. The big magnetic field is going to be around this electromagnet because all of the little magnetic fields around each section of wire are going to add together. And they're going to form a much larger and more significant magnetic field. So honestly, if I give you a problem like this on the exam, I wouldn't actually care if you draw the magnetic fields in this section and in this section because they're pretty inconsequential. I'm only doing that to kind of show you some practice and to kind of demonstrate what's going to happen as we start to wrap this around. All I really care about is the magnetic field that's surrounding this electromagnet. That's the relevant magnetic field. All right, so what you can think about is this magnetic field around this conductor, and it's going to get wrapped around this core material. All right, so we've got this wrapped around in back of the core material first, and then coming around in front, and then going back behind, and then coming around in front. So the direction that current is flowing through these sections of wire, remember current's going this way, so it's going behind the conductor and then going this way. So it's going right to left in this section of wire, and then it goes behind, and then it comes around again, and it goes right to left again. So it's going behind the core, and then it's always going from right to left through these sections of wires. All right, so through all of these, the current is going from right to left. All right. So the current is going from right to left, so we apply our right-hand rule for current-carrying conductors like this, because the current is flowing like this, and as I wrap my fingers around the conductor, and think about doing this for all of these conductors right here, and that magnetic field is going down behind these wires, or down through the middle of this electromagnet, and then up around the outside. So it's going down through the middle of these conductors, down through the middle of this core material, and then up around the outside of these conductors. And that's true for all of these wires, and it's even true for the wires in back of the core material too. If you kind of wrap your hand around, it's kind of hard to do, but you can see that for all of these wires, every segment of wire around here, the magnetic field is going down through the middle of the core and then up around the outside. So our magnetic field looks something like this, and we said that the magnetic field is going down through the middle and then up around the outside. So the direction looks like this. Remember, they don't intersect, and they always go from north to south. So automatically, we already know which side is the north side and which side is the negative side. Okay, I guess I probably shouldn't have drawn these two because I told you they didn't intersect, and they don't. So ignore these two for right now. Our lines of magnetic flux should not intersect. All right. And we know that the direction is always from north to south, and this is going from this side to this side. So this must be the north side, and this is the south side of the electromagnet. All right, so for number 2, we are asked, which direction is this generator rotating? And to do this, we have a relationship between the direction of the current flow and the magnetic field and the direction of motion. And that relationship is given by the right-hand rule for generators. So I like this set of examples because this one you have to apply the right-hand rule for current-carrying conductors. It looks like this. And in number 2 here, we need to apply the right-hand rule for generators that looks like this, where your thumb, your first finger, and your second through fourth fingers are all perpendicular to each other. And if you recall from last time, the first finger is the direction of the field from north to south. The second through fourth fingers are the direction of current flow, which is caused by the induced voltage. And the thumb is the direction of motion of the conductor at that point in time. All right, so we can go ahead and apply this, and the way we're gonna do this is we're gonna fit two of them and then find the third. Anytime you have two of those three, you can find the third by applying the right-hand rule for generators. In this case, we are given the direction of the magnetic field, and the direction of the magnetic field, I'll go ahead and draw it in this time. It's from north to south. So it looks like that. So clearly at this point in time, when our armature is horizontal, our first finger needs to go from right to left. So we need to have this finger pointing from right to left. And then we will apply the right-hand rule to each side of the armature in turn. So it really doesn't matter which side we do first. Let's do the right side first, the right side of the armature, or the coil of wire. So our first finger goes from right to left, and then our second through fourth fingers need to face in the direction of current flow. And this is kind of the tricky thing. The tricky thing is that this is meant to represent a three-dimensional object, but we're drawing it two-dimensionally. And so the tricky thing is to remember that when we're drawing something like this with the current flow, this current flow is actually coming out of the board or out of the page. And that current flow is going into the board or into the page. All right, so just keep that in mind as we're doing these things. So our first finger goes right to left. Our second through fourth fingers are coming out of the board. The way I've tried to draw that three-dimensionally, it's coming out of the board. So that leaves our thumb pointing up toward the top of the page. All right. It's also a little bit inadvisable to use the word up, honestly, because up could mean up toward the top of the page this way, or it could mean up out of the page. So you got to be kind of careful about that. And I need to be careful about that as I'm talking about it. So in this case, this is the situation on the right side of the armature. The field is pointing right to left. The current is coming out, up out of the page, or up out of the board towards you, towards the camera. And my thumb is pointing up towards the top of the page. Right? So this is pointing up like this towards the top of the page. Now we apply the same thing to the left side of the armature. It should be consistent. And so I would expect that if this is going up, then this is rotating like this. And so this is probably going to be pointing down towards the bottom of the page. But let's see. So our field is going from right to left still. And now our second through fourth fingers, which we align with the current, are going into the page or into the board. And that leaves our thumb pointing down towards the bottom of the page, kind of like this. All right, so this side of the armature is pointing down towards the bottom of the page. So if this thing is rotating, and this side's going up right now, and this side's going down right now, then this thing is rotating like this, around in this direction. In that direction, and that direction is counterclockwise. All right, so this generator is rotating counterclockwise right now. Okay, now let's move on to number 3. So we've got this generator right here. The only important thing to note here, when in number 3, when it says the generator in problem number 2, the only thing that we really have to pay attention here is how many turns are in the coil. And the way we've drawn it, we've only got one turn in this coil, which is totally unrealistic. A real generator would have hundreds to thousands of turns in the armature or the coil. But in this case, we've drawn it very simply, and so it's only one loop, which we say is one turn. So it's only got one turn in that coil. And we've got that generator, and we know the change in magnetic field. So it goes from this to this. So this is going to be B1, and that's going to be B2. The magnetic field initially and the final magnetic field. That's going to be our delta T, because it takes 0.1 seconds. We're given the area of the coil. In a lot of these problems, you won't usually be given the area of the coil. You might have to calculate it. So remember, the area of the circle is pi r squared, but it won't always be a circle either. It could be a rectangle or a square. So remember, the area of a square is the side length squared, and the area of a rectangle is the length times the width. So you might have to use those. Also remember that the area is always going to be in meters squared. If we're using the units that we've talked about, and we're using Webers for magnetic flux, then the area is always going to be in meters squared. All right, so we're trying to find the output voltage. So clearly, we're going to use our equation that gives us a relationship between the number of turns, the magnetic field strength, the time, and the area, and that equation is Faraday's law. So that's clearly the equation we're going to use here. So here's Faraday's law, and I like to write down the things that I know. So I already know that N, that's the number of turns, equals 1 turn. The change in time is 0.1 seconds. And I can calculate the change in magnetic flux. I don't know it right away, it's not given, but I can calculate it because the change in magnetic flux is the magnetic flux at time 2 minus the magnetic flux at time 1, which is B2A2 minus B1A1. A1 is equal to A2. The shape of the armature doesn't change. And so I can factor that out and just call it A. And what's left after I factor that out is B2 minus B1. And I know all of these things here. So I can plug all those in. My area is 0.2 meters squared. B2, that's the magnetic field that it is going to at time 2. That is 1.5 Teslas, and the initial magnetic field strength was 0.5 Teslas. So now I can do that calculation. I can do that one in my head, actually. 0.2 times 1, because 1.5 minus 0.5 is 1. So I'm left with 0.2 Webers. And now I can plug everything into Faraday's law. Don't forget the negative sign there. If you end up with a negative voltage, which is what we're going to do here, it's no problem. Just leave it. It's no problem. Because the voltage, remember, is positive for half a cycle, and then negative for half a cycle, and then positive, and then negative, and so on and so forth. So it's no problem at all to have a negative voltage. Just leave it in there. In fact, if it should be negative and you write a positive number, it's actually wrong. So make sure you leave the negative sign in there. So we have negative, because that's what the equation says, times 1 turn for N, times 0.2 Webers for delta phi, divided by 0.1 seconds for delta t. And this is a pretty easy calculation. 1 times 0.2 divided by 0.1 just gives us 2. And don't forget your negative sign, so it's negative 2 volts. So the induced voltage here in number 3 is negative 2 volts. All right, so hopefully that helps kind of refresh your memory a little bit from what we were talking about last time. And in the second video for today, we're going to cover some new material, and we're going to talk about some additional applications and components from generators.